Okay, I'll start talking about the percent composition of saturated sodium chloride solutions at various temperatures lab. And what I'm going to do is I'm not going to go ahead and read everything, but I'll kind of skim over the topics or the points that are being made, okay? We are talking about solubility, and solubility focuses on a solute, a solute dissolving in solvent to form. Oh, this is out of frame. Hold on. Let me make this smaller. A solute dissolving a solvent to form a solution. Okay. The solute tends to be in the lesser amount. The solvent is the greater amount. And the two together combine to form the solution. Okay. Once we have defined that, we're now looking at, the other term for solution is a homogeneous mixture, implying that when you make that solution, when you finally make that solution, it's difficult to tell that the solution is made up of more than one component. You cannot visually tell that there's more than one chemical in there without experience or prior knowledge, okay? The next thing we're defining here is the unsaturated versus saturated solution, okay? Each solvent, as long as the solvent is a specific amount, can dissolve a certain amount of solute. Okay, and I'm going to stick with the solute and the solvents that are pretty much. Wait, am I sharing? I think I'm sharing, right? I get these moments where I'm like, I can't see. Okay, yeah, your screen share. Okay, woo. Okay. So where was I? Yeah, unsaturated. Let me give you an illustration of unsaturated solution. We're told here the unsaturated solution contains less than maximum amount of solute. So this is an example. Let's say that you are working with 100 grams of sugar. Okay, 100 grams of sugar, right? And your 100 grams of sugar has to dissolve in something. So you say 100 grams of sugar dissolves in 1,000 grams of water. That's a lot of water and a lot of sugar, right? This is sugar water, okay? And this is a statement of fact. So this is a solubility. So you can get up to 100 grams of sugar to dissolve in 1,000 grams of water. This is a made-up number, okay? But then you manage to dissolve 50 grams of sugar in 1,000 grams of water. This solution you make will be unsaturated just because you have room for 50 more grams of sugar in that water. The water has not reached its maximum capacity of solubility. It can still take in 50 more grams of sugar, okay? If that's unsaturated, then what is saturated? To have a saturated solution, we're told right here, the saturated solution will have the maximum amount of solute dissolved in the solvent, right? But sometimes you will also have some undissolved solid in that solution. So a saturated solution has maximum amount of solute in solvent, okay? So imagine you got 100 grams of sugar and 1,000 grams of water. That is considered saturated. You have reached that maximum amount that's possible, right? You have got to that number, and that magic number is 100. 100 grams of sugar and 1,000 grams of water. Okay, now that we've said that, but we're told here, even in a saturated solution, some of the solute falls out of the solution or the solvent and becomes undissolved. So you see that right here? So when you're making your solution, make sure you do have some undissolved. Like keep adding the salt until you have some undissolved solid. And as long as you have undissolved solid at equilibrium with the solution, then you know that you have the maximum possible amount of the solute in the water. Okay, so if you keep adding this, in our case, of course, your experiment is salt and water. When you're making your solution, keep adding salt. Okay, you're gonna add salt, stir, stir, stir. You will get to a point when you add salt, the new salt you added will not dissolve. When you reach that point, you have actually reached saturation. That means in the solvent, you have the maximum amount of salt that solvent can hold. Does that make sense? Okay. So we're told in general, when you're trying to dissolve, there are three main factors we're looking at here. These are rules of solubility. Rule number one, the physical state of your solute matters. Okay. Is your solute a gas? Is it a liquid? Or is it a solid? I'll say here, or solid, right? In our case, we're dealing with table salt. So in our case, our salt or table salt is a solid. Okay. The solubility factors in the physical state of your solute. It's a lot easier to dissolve a gas. Well, I shouldn't say there's a catch-22 here. You can dissolve a gas in a liquid, like when we have soda, right? A liquid in liquid with like drinking alcohol, or a solid in liquid, like what we're going to be doing, which is salt and water. Number two, so I'm kind of paraphrasing from here. I just did that part. The second part is polarity. Okay. If you have a solute that is polar, and I'll come back and explain number one a little bit more when I get to number three. If your solute is polar, then your solvent has to be polar to form a solution. Okay. Now, if your solute is nonpolar, then guess what? Your solvent has to also be nonpolar. Okay, I'm getting close to the end, right? And then number three is the factor of temperature. So before I get to number three, I want to talk about the liquid. So we're going to be looking at solid in liquid solution. In our case, well, we're talking about polarity. So before I get to number three, in our case, salt is ionic, right? It's not really polar, but ionic is also known as extreme polar. So we're told here sodium chloride is an ionic salt, which is polar. It's an extreme polar, right? So ionic, we'll call this extreme polar. So our ionic solid can dissolve in water. Water is just regular polar. Technically, the interaction that allows them to dissolve in each other is called ion dipole, but that is beyond the scope of this classroom or this class, right? So bottom line here is we're looking at sodium chloride dissolving in water. Sodium chloride is extreme polar, water is polar. And so the sodium chloride solute can dissolve in the water solvent. Okay. Okay, so we're talking about the solid. With the liquid, same thing. As long as the liquid is polar and the solvent liquid is also polar, a solution can form. When it comes to gas, things get a little bit complicated, right? So I want to talk about temperature right here, and then I'll talk about gas with the temperature. In the case of temperature, we see a general rule, and this rule I'm telling you guys about applies to solids. So temperature, we're looking at solid solute in liquid solvent. I was about to say water. Liquid solvent. Okay. When you have a higher temp, we expect to have a greater solubility. And when you have a lower temp, we expect to have a lower solubility. Once again, it says so here, as the temperature of the solution increases, the solubility of the solid solute increases, while the solubility of the gaseous solute decreases. So I want to mention that this rule works for solid, but if you have a gaseous there, solute in liquid solvent, we notice the opposite. In gases, higher temp causes lower solubility. If you want soda to go flat, so soda is an example of a gaseous solute in a liquid solvent, right? You have the carbon dioxide that was bubbled into the liquid to make it tart and bubbly and have all the fizzing. If you leave the soda out in the heat, the carbon dioxide molecules in the solution gain energy and they try to escape the heat. Okay, but if you put that bottle of soda in the refrigerator, it actually increases solubility. So lower temp works better for gases. Lower temperature increases solubility. So this is more like a FYI, right? Just random information. But this part doesn't apply to our lab because our lab is a solid solute in a liquid solvent. So now we are ready to work on the lab. Finally, you need to make sure you have all of the following items. I won't go through all of this. And so we're told here, place 100 milliliter of tap water into each of 3 small drinking glasses and label them A, B, C. So I'm going to draw a mock diagram of all of these, right? So direction number 1, you're gathering, I'll just say gather items. Direction number 2, we have drinking glasses and they're labeled A, B, C. Imagine they're the same size. I don't know why they're getting smaller. I think I'm becoming aware I'm running out of space. And then they're telling you to add sufficient salt to each container while stirring until there is undissolved salt at the bottom, saturated. So this is the part I was talking about earlier, right? When you first add salt to water, when you're stirring this, the salt will dissolve. That means you're dealing with an unsaturated solution. Keep adding the salt and keep stirring. What we care about is the salt dissolved in the liquid, not the one at the bottom. But we want to make sure the liquid is carrying the maximum amount of salt it can carry. We want it saturated, right? So the only way for us to know we have reached that level is to keep adding salt. So keep adding salt, stir, keep adding, stir. If you are stirring and the salt can still dissolve, you have not reached maximum saturation level, okay? Saturation level is when the liquid says, okay, I've had enough of the solute, I can't take anymore. It's like being full, right? Like, yeah, being full. Anyway, so you want a saturated solution, the liquid part. So when you get to saturation, you cannot dissolve any more solid. So there'll be some solid left on the bottom here, undissolved. That's okay. We're not going to mess with that. All we care about is the liquid. And then we're told, place container A into an ice bath. So I do have some pictures here. Let me see. Did I follow the directions? I don't think I did. No, I did. They're right here. I did. They're right here. Okay. Do I have, okay, I do have some words here, but this is it right here. So you can see my beakers with the salt in there already dissolved. So I've already stirred it up and I have some excess salt swimming around. I don't really care about that. And it says right here, add sufficient salt while stirring until there's undissolved salt in the bottom. So that part is done. 4, place container A into an ice water bath. So that's what I did here. I had ice in here and I placed my solution, right? I placed my solution in there. So you're going to place A. This is number 4. This is number 3 right here in an ice water bath. So you're going to have pieces of ice cubes around here. Okay. And you're going to keep stirring to make sure it dissolves, right? And then place container B. So this is ice water. Place your container B, which is your glass. And it says here, what is it? Room temp. Room temp. And so you have the solution here with your undissolved salt in the bottom. Place container C. I'm assuming this is going to be hot water, right? Right. So tell you here, make a hot water bath by placing about 200 milliliters of warm tap water into a 600 milliliter beaker. So this should come with your lab kit, right? And set it on the stove burner at the lowest setting. So you want to get some hot water. So this part here, this would be hot water, but you're going to place it on the stove and place it at the lowest setting. So the goal is to heat up the hot water to influence the temperature in here so it can influence the solubility, right? The purpose of this water bath is to keep the container C at a constant temperature. So you want to keep it at the lowest setting on your stove burner and keep it at that temperature, okay? So here it says, place container C into a water bath containing warm tap water. Don't we already have it in the warm tap water? Oh, you know what? This is where we're here. Okay, so my bad. Direction 6 tells us how to create the hot water bath. We're placing 200 mils of water in 600 milliliter beaker and setting it on the hot stove. We haven't placed the container in the beaker yet, right? They're telling you why you're doing that in number 7. Number 8 then says place container C into a water bath containing the warm tap water. So I think somewhere here in my picture I have C. Oh, there it is. Oh, I took these pictures a long time ago, so I have to rediscover them. There it is. Okay. Then let the solution stand for 10 minutes. During this time, stir the solutions to guarantee they remain saturated. Right. You want the liquid part to hold on to as much solute as it can at that temperature, right? So keep stirring to give that liquid a chance to be at saturation level. At the end of the 10-minute wait, measure the temperature of the solution in container A. So this is you seeing me and my student working on that part. So we are measuring the temperature of the solution, not the water, in container A. It says using a dropper and a 10 milliliter graduated cylinder, draw out about 1 mil. So they're saying draw out 1 mil. So you want to draw out 1 mil, right? Use the dropper, but you're going to use the cylinder. So the cylinder right here, let's see. I'm going to draw the picture because I don't want to go back and forth. Let's say this is your cylinder right here, right? And there's a mark that says 1 milliliter. You're going to use a dropper to add 1 milliliter. So this is you adding drops until it reaches that 1 milliliter mark. Okay, where was I? Right here. From container A, and place the sample into a previously weighed test tube. So you want to make sure you label your test tubes, right? Weigh your test tube and then label them. So it says previously weighed test tube. Record the weight of the test tube plus the solution. Okay, so you have gone ahead and weighed your test tube. You have the weight of the test tube is already done. And then the next thing you're going to do is you're going to add solution. So you have weight of test tube. You're going to add solution. And you're going to have weight of test tube plus solution. Because now you have two things, right? I'll put SOL for solution. And then you're adding that to the test tube. And you're going to weigh this again according to the directions. Record the weight of the test tube plus the solution. And then it says, light the flame of the alcohol burner, grasp the test tube with the test tube holder, and tilt the test tube slightly swaying from the vertical angle and move it back and forth in the flame, heating the solution from the top down. Okay, so I think I have a picture here showing someone heating. Oh, this is my student adding, she already added the liquid to the 1 milliliter mark in the graduated cylinder, and she's pouring it now in the test tube that's marked 1. Okay. And then I think there's a picture here. Oh, This is where she's weighing the empty test tube. Oh, I guess we're missing one where she weighed it with the solution. This may be it. It's really hard to tell. Oh, yeah. Okay. So you have to have weighed the test tube by itself empty, right? And then here we're weighing the test tube and the solution. So that's what was done here. And then she took this and put it over the flame. Now we were doing this in the lab, so we have access to the Bunsen burner flame. You're going in and out and in and out of that flame, right? Okay, where am I? Yeah. Continue heating until the residue in the test tube is dry. So you want to go in and out until the residue in the test tube is dry. So all the liquid will burn off and it'll be evaporated, and you will have just a dry crust, right? Dry salt on the bottom. An indicator of dryness is a lack of water droplets. So they're telling you when you're heating this, make sure you're heating the walls of the test tube also, because sometimes the water evaporates, but then it doesn't leave completely. It sits on the walls of the container. You want the whole test tube to be dry. That's what they're saying. Continue heating until the residue in the test tube is dry. An indicator of dryness is a lack of water droplets condensing at the mouth of the test tube. That means all the way up here should be dry. Let the residue cool and weigh the test tube plus the salt. So once you're done drying everything, you're gonna sit this down, right? And let it cool. While it's cooling, you're gonna repeat the process with the second test tube. So you see here, I have labeled my test tubes 1, 2, and 3. And what I did is I weighed 1, wrote the weight of the test tube down, added solution, weighed that, evaporated the water out, let it cool. I started with 2. Repeat the same process, right? Record the temperature of the solution because it might have changed. You don't know. Record the temp, draw out 1 mil, weigh the test tube, add 1 mil of the solution to the test tube, weigh the solution and the test tube together like we did before. Go ahead and heat this up. Oh yeah, weigh it together, heat this up, evaporate the second one, same temp, right, as the first one. So we're dealing with the ice water first. So remember, with the ice water, you're gonna have 3. Oh, I forgot, I'm back to working on this. With the ice water, you're gonna have 3 test tubes. So I have them labeled as 1, 2, 3 in my pictures. Remember, these are A1, A2, A3. And in each case, you're drawing out 1 mil of solution. Don't draw out the solid. All we need is a solution, right? The liquid part. Draw out 1 mil. And then you're going to, of course, heat each of them. Evaporate to dryness. Make sure everything is dry. Your test tube is completely dry. And then go ahead and do this, make sure each temperature, ice water, room temp, or hot water, produces 3 samples, okay? And then you're gonna let the residue cool and weigh the test tube plus salt. So once you take this and then you, of course, heat, I'm gonna just show you one test tube, 1A. You will have dry samples right here, and this is 1A. You're gonna weigh this. Okay, so let me give some numbers for this to make sense. Let's say the test tube by itself is 10 grams. Okay, and then let's say test tube plus solution is 11 grams. And then when you're done weighing this sample, okay, when you dry this out, you weigh test tube, this is the 3rd time, plus dry residue. So you weigh this and you get, let's say, 10.5 grams. Now you go to your table and complete the table. So you're told to repeat steps 8 for 2 more samples of A. I've already talked about that. A2 and A3, correct? And then perform the same steps 8 to 9 for the solutions in containers B and C. So you started off with a cold water solution, got 3 from that. Do the same thing for the hot or room temp, you get 3 from that. And then hot water, you get 3 for that, okay? So each of the temperatures produces 3 samples. record all data in the following table. And it says to calculate percent of salt in the data, divide weight of salt over weight of solution multiplied by 100. So we have our table right here, okay? Let me see what else I have in this picture. Let's see, we have that. This is me heating. Oh, I show you guys an alternative method. I do say that if you're at home, I shouldn't say if you're at home. Since you are at home, if you have a gas stove, you have access to an open flame that's a lot hotter than the alcohol burner you have in your kit. If you feel safe enough, it's not a must, right? But remember, that can be dangerous. If you feel safe enough, you can use your gas stove at home, like a Bunsen burner, and it will heat faster. If you don't feel comfortable with that, or you don't have a gas stove, the alternative method is to use your hot plate at home, like I'm using this hot plate in the lab. Your electric stove has a hot plate. You can sit the 3 test tubes, because this will take a lot longer, in a beaker, and then sit close by, turn it on, maybe medium, definitely not high, because it'll start popping a lot. Turn this medium. Actually, you know what else you can do? You can even add some water to this, because the water will get hot and the water will actually heat the water in the test tubes and start to evaporate them. Okay, that will take a little longer. If you do the direct contact, that will actually heat it faster. But bottom line is, the hot plate can be used to evaporate the water from all 3 test tubes. It will take a longer time to do this process. Okay. So, here's where I show you the math. Anyways, let me go back to this part here. So say we have the samples, right? And in my example here, I have to go weight of test tube. Do I have a table? Let me draw a mock table. I'll copy this table I have on my left. Okay. So we have A1, A2, A3. And I have weight, test tube, test. This is weight of test tube and solution, right? Then you have weight, solution, temp. I'm running out of room. You know? You think you have a lot of room, and then you realize you don't have a lot of room, and then you're sad. Okay. Let's see. This is weight, temp, test. Oh, this is temperature. Oh, okay. This is just temperature. And then weight of test tube plus salt. And then weight, salt, and then percent salt. Ooh, barely made it, y'all. Barely made it. I don't know why my handwriting slants that way, especially after a long day. Anyway, bear with me. So you get the idea, right? I'm just going through here. Okay, so I'm going to use my fake numbers. These are not the real numbers, so don't use those numbers. Let's see. Weight of test tube I said was what? 10 grams, right? So 10 grams right here. And then weight of test tube plus solution. That's this one right here, 11 grams. So with a solution, take this minus this, right? So 1 gram. Temperature, if it's cold, let's say 0 degrees Celsius. Now, let's say, I'll pick a number, not 0. Let's say 5 degrees Celsius. Weight of test tube and salt. That's the dry residue right here. 10.5 grams, right? Weight of salt by itself. It's going to be this minus this. So 0.5 grams. So what's my percent salt? In my case, percent salt will be this mass over the solution times 100. So it's going to be 0.5 grams over 1 gram times 100. So I'm going to have 50% here. So you're doing this 3 times. So let's pretend all 3 are 50%. Okay. And then down here, it says calculate the average concentration for each of the different solutions. So the average, of course, would be 50 plus 50 plus 50 divided by 3 to give you 50. Then it says using an Excel spreadsheet, prepare a graph of percent salt. So you have a graph of not the individuals, but the average, because that's why you got the average. You're going to plot 3 points only. So you're going to draw a graph of percent salt. They should have said average percent salt over temperature in degrees Celsius. And you should get your graph here, and it says paste the graph in the space below. Do you have to figure out the equation? Okay, so let's say that this is what you got, right? This is not right. Let's say you got, it's going to be a linear graph. Say you got that relationship. And it says formulate the hypothesis about the solubility of sodium chloride in water and enter the space. Formulate a hypothesis about solubility of sodium chloride in water and enter it in the space below. So as temperature in degrees Celsius increases, comma, how does the percent salt respond? Or how does the solubility? Remember, percent salt here represents solubility. Just in case you felt like our purpose was lost, it wasn't. Percent salt represents solubility. So when the temperature goes up, what do you expect to happen to the solubility? Do we have more solubility or less? Okay. And here they're asking you, based on your graph, estimate the solubility of sodium chloride in water. So part B says, estimate the solubility of sodium chloride in water that has a temperature of 40 degrees and enter it below. Okay, this statement is unnecessary. It should have been just given to you. Anyway, so let's say you have a temperature of 0 degrees Celsius, you have 5 degrees, you have 10, you have 20, you have 30, you have 40. You're going to look at the temperature of 40 and then read across. And the number you get here will tell you of the solubility. Once again, guys, sorry, it's been a long day. I'm just trying to get this video done, okay? It's been a long day, so hopefully this makes sense, okay? I try to explain to you how the lab is set up and how it works. So hopefully this makes sense, and then you can use this and finish up the lab. This is a whole different lab, right? Okay, have a good evening.